Okay, section 3.2, we have trig integrals. So this is going to be integrating trig functions and products of trig functions. So first of all, we're going to start off with products and powers of sine and cosine x. And then we're going to be looking at products and powers of tangent x and secant x. So this is going to bring back all of those trig formulas that we worked on in advanced math last year. So if you have that chart, oh, I'm going to post one of those too. I can't forget to do that. So all of those will come in handy here. So we're going to be integrating these. So let's look at a couple review. So this is right from your trig identity sheet from last year. Remember our Pythagorean identities that we used? We mostly used this top one here. All right. We're also going to be using this one a lot too. So it'd be really nice to have those both memorized, and any form of them. The way that we're mostly going to use these is in the form of sine squared theta is equal to 1 minus cosine squared theta. And cosine squared theta is equal to 1 minus sine squared theta. Okay, that's how we're going to use these top two mostly. And then this one here, we have tangent theta plus 1 equals secant theta, so that's good to know. We want to know what secant squared theta equals. And that equals tangent squared theta plus 1. And then tangent squared theta is going to equal secant squared theta minus 1. So all four of those identities you're going to want to be able to easily come up with. Then also we're going to use some of these double angle formulas. The main way that we're going to use them is in a way that it's a power reduction, and we talked a little bit about this last year, power reduction formulas. And you can use these equations, mostly this one and this one. So we can solve for cosine squared of A by saying that cosine squared A, so we would add 1 to this side and then divide by 2. So it would become 1/2 plus 1/2 cosine of 2A. And then we would do the same thing to solve for sine squared of A. And we'll have that later on too. But those are your main identities that we want to use throughout part 1 and part 2 of 3.2. So let's move on and we can look at some of the examples that we have. All right, for example number 1, it says evaluate the integral of cosine to the 5th x dx. On these ones, we don't have any way to do products of so many trig functions. So we want to look at some different identities and some different ways to write these. One thing that we could do is, okay, so well, what if we did a substitution for cosine, said u equals cosine of x. That would give us the integral of u to the 5th, which we could do. But what's the problem? The problem is that what is the derivative of cosine? Well, the derivative of cosine is negative sine x dx. And we don't have a sine in there. So if we want to do some kind of a u substitution, we also have to have a sine function in there. So what I'm going to do here is I'm going to start peeling this away. We can rewrite this as cosine squared x, all squared. That gives me 4 cosines, so let's do times 1 more. So I'm just going to start breaking up these cosines in ways that I can go back and rewrite them using the formulas that we just looked at. So the reason I want this cosine squared is because I can rewrite that as 1 minus sine squared x. And then we know that if we can do a substitution, in this case we're going to end up doing a substitution of sine x. We don't have a sine yet, so that's kind of hard to see, but that's where we're headed. Okay, so we've got this written. This is still cosine to the fifth x. Now we want to rewrite what's inside the parentheses. So let's go with 1 minus sine squared x all squared. Right? And we still have cosine of x out here, dx. And then I'll tell you another little hint. It always seems like whatever's kind of left off, whatever gets peeled off and left in the end with our dx is usually what's going to end up being du. And now in this case, I have 1 extra cosine dx. So that's what I want du to be. So if I want du to be cosine, that must mean I want u to equal sine, which I just started talking about up here. So if we say u is equal to sine x, then du is going to equal cosine x dx. Okay, so now let's go back and rewrite that integral. So now we have the integral of 1 minus u squared all squared, and then that all becomes du. Okay, so now we've got some multiplication to do here. Let's go ahead and multiply that all the way out. So that's going to become 1 minus 2u squared plus u to the fourth du. And then we can go ahead with our integration. So once we integrate, we'll get u minus 2/3 u cubed plus 1/5 u to the fifth plus c. And then we need to substitute back in for u. So we have sine x minus 2/3 sine cubed x. And actually, I want to not put in that parenthesis. Not that it really matters. I just think it looks cleaner without it. Sine cubed x, and then what were we? Plus 1/5 sine to the fifth x plus c. And then that's our final answer. Okay, this one is the identity that we were just looking at before, what we call, it's a half angle identity, but we can also call it a power reduction. So it's cosine squared x equals 1/2 plus 1/2 of cosine 2x. Okay, that's the way I'm going to use that one. So we've got the integral of cosine squared x dx. And the main difference between this one and the last one, and this is really important with all of these, is that you notice whether or not the exponent is even or odd. So if it's an even exponent, in this case, so we have squared, then we need to use an angle identity like this, the power reduction, because we don't have that extra cosine that we can peel off of there to go with our du. So the last one was to the 5th degree. So one with the 5th to the 5th degree, we had an extra cosine that we could peel off of there, and it could go with the du. So if this one would have been cosine cubed, I would have peeled off cosine squared and a cosine, and just a single cosine, and then that cosine dx could have been my du. But in this case, if I tried to peel off a cosine, I would just have one single cosine, another single cosine, and I wouldn't get anywhere with it. So when that happens and we end up with an even exponent, then it's these kind of identities that we need to use to simplify our trig function so that we can actually integrate it. So we know cosine squared x equals 1/2 plus 1/2 cosine of 2x. So we're going to switch that over. So integral is now we're taking the integral of 1/2 plus 1/2 cosine of 2x dx for all of it. And we can go ahead and integrate. So 1/2, actually we never even did use substitution, did we? So 1/2 x plus, now we've got a 1/2 out in front, that's just going to stay there. And then we're going to end up with a 1/2 from inside here also for our chain rule. So 1/2 times 1/2 cosine of 2x. And then plus c. So final answer is 1/2 x plus 1/4. Oh shoot, I didn't integrate it. Sorry. We do need to take the integral of a cosine. Okay, which is then sine. So 1/4 sine of 2x plus c, and then we're done. Okay, for example number 2, we have an odd sine function, have an odd cosine function. That cosine is kind of off all by itself, so I want to see if there's a way that, I can make this cosine x dx be my du. Oh. Okay, so I'm just rewriting this in a few different ways. So I've got sine squared x all to the square, and then actually, you know what? I don't even think I need to do all of that because I already have my du. Yeah, so I don't even have to do that much. That's what I did when I was working through this problem, but I didn't even have to do that. So I could just say u is equal to sine x because I already have my du, which is cosine x dx. Yeah, that's all I have to do. So I don't even need all this. Let's get rid of all that. And so now all I'm doing is integrating u to the 5th. Okay, so then that becomes the integral of u to the 5th, and then all my cosine x dx goes to du. And so we get 1/6 u to the 6th plus c, which then is 1/6 cosine x plus, cosine to the 6th x. Oh, why cosine? Okay, I'm not doing so good this today. Our u is sine x, so we have 1/6 sine to the 6th x plus c, and then that's your final answer.